Welcome to the chapter on thermodynamics. Understanding the principles of thermodynamics is essential for analyzing and designing systems that involve energy transfer and transformation. In this chapter, we will cover the first law of thermodynamics, the second law of thermodynamics, and the different modes of heat transfer. The first law of thermodynamics, also known as the law of energy conservation, states that energy cannot be created or destroyed, only transferred or converted from one form to another. Mathematically, it is expressed as delta U equals Q minus W. Here, delta U is the change in internal energy of the system, Q is the heat added to the system, and W is the work done by the system. Consider a gas in a piston. If 500 joules of heat is added to the gas and the gas does 200 joules of work by expanding the piston, the change in internal energy of the gas is calculated as delta U equals Q minus W, which equals 500 joules minus 200 joules, resulting in a change of 300 joules. The second law of thermodynamics introduces the concept of entropy, a measure of disorder or randomness in a system. It states that the total entropy of an isolated system can never decrease over time. In other words, natural processes tend to move towards a state of maximum entropy. One of the most common formulations of the second law is the Clausius statement, which asserts that heat cannot spontaneously flow from a colder body to a hotter body. Another formulation is the Kelvin-Planck statement, which states that it is impossible to construct a device that operates on a cyclic process and produces no effect other than the transfer of heat from a single reservoir to work. Consider a refrigerator. It extracts heat from the inside, which is the cold reservoir, and expels it to the outside, which is the hot reservoir. According to the second law, this process requires work input, such as electricity, to transfer heat from cold to hot, aligning with the Clausius statement. Heat transfer is the process by which thermal energy moves from one object or substance to another. There are three primary modes of heat transfer: conduction, convection, and radiation. Conduction is the transfer of heat through a solid material. It occurs when molecules in a material collide with each other, transferring kinetic energy. The rate of heat transfer by conduction is given by Fourier's law, which is Q equals negative K A dt by dx. Here, Q is the heat transfer rate, K is the thermal conductivity of the material, A is the cross-sectional area through which heat is transferred, and dt by dx is the temperature gradient. Convection is the transfer of heat by the movement of fluids, which can be liquids or gases. It can be natural, due to buoyancy effects, or forced, using fans or pumps. The rate of heat transfer by convection is given by Newton's law of cooling, which is Q equals HA times Ts minus T infinity. Here, Q is the heat transfer rate, H is the convective heat transfer coefficient, A is the surface area, Ts is the surface temperature, and T infinity is the fluid temperature far from the surface. Radiation is the transfer of heat through electromagnetic waves. Unlike conduction and convection, it does not require a medium. The rate of heat transfer by radiation is given by the Stefan-Boltzmann law, which is Q equals epsilon sigma A times T to the power of 4 minus T infinity to the power of 4. Here, Q is the heat transfer rate, epsilon is the emissivity of the surface, sigma is the Stefan-Boltzmann constant, A is the surface area, T is the absolute temperature of the surface, and T infinity is the absolute temperature of the surroundings. Consider a metal rod with one end heated to 100 degrees Celsius and the other end at 25 degrees Celsius. If the rod has a thermal conductivity of K equals 200 watts per meter Kelvin, a cross-sectional area of A equals 0.01 square meters, and a length of L equals 1 meter, the rate of heat transfer by conduction is calculated as Q equals negative Ka dt by dx, which equals negative 200 watts per meter Kelvin times 0.01 square meters times the temperature difference of 100 minus 25 degrees Celsius divided by 1 meter, resulting in negative 150 watts. The negative sign indicates that heat flows from the hot end to the cold end. In summary, the first law of thermodynamics deals with energy conservation. The second law introduces the concept of entropy and states that natural processes move towards maximum entropy, and heat transfer occurs through conduction, convection, and radiation. This concludes our chapter on thermodynamics. Understanding these concepts is crucial for analyzing and designing systems that involve energy transfer and transformation. Thank you for your attention.